Good afternoon. Welcome to the webinar on Introduction to the Integrated Northern Tampa Bay Model. Thank you for joining. My name is Jeff Goering, Lead Water Resources Engineer with Tampa Bay Water. I will be the presenter. The Integrated Northern Tampa Bay Model, which I will refer to as the INTB model, was developed as a partnership between Tampa Bay Water and the Southwest Florida Water Management District. The Southwest District is one of 5 water management districts in Florida. It has authority to regulate water use throughout a 16-county area in West Central Florida. Tampa Bay Water is a wholesale potable water supplier to 6 member governments in the Tampa Bay area, serving 2.5 million people. Tampa Bay Water holds several water use permits with the Southwest Florida Water Management District. The INTB model is used extensively by both agencies and others in the region to support water management decisions. The Integrated Northern Tampa Bay, or INTB model, simulates all processes and the water table feedback amongst uplands, water bodies, and the groundwater system. It covers 4,000 square miles over the central part of the Southwest Florida Water Management District, encompassing 8 major river watersheds and 3 groundwater basins. It simulates all the dynamic surface water groundwater interactions in this region. The webinar outline will include these points: general characteristics of a fully integrated hydrologic model, discuss briefly a specific model called the Integrated Hydrologic Model, or IHM, simulation engine. Then we'll talk about the specific characteristics of the INTB model, including motivations for development, conceptual foundations, numerical model, and example applications. And we'll take 4 breaks for questions. First segment on fully integrated models. General characteristics of models like these completely simulate the hydrologic system of all uplands, water bodies, and groundwater, and its dynamic interactions. Also includes the water table feedback mechanism that can influence runoff, evapotranspiration, and recharge. Integrated models also replace the interfacial boundary conditions that are used for single regime models with dynamic simulation. Surface hydrology. Examples of these boundary conditions that are replaced include depth to water table and base flow. Examples for a groundwater model include recharge rate, max ET rate, water body stage, and specific yield. These fully integrated models simulate all processes in the water table feedback for surface hydrology, ET in the vadose zone, and groundwater hydrology. Now it's instructive to take a look at the differences in fluxes between deep versus shallow depth to water table conditions. The blue box that you see on the screen shows vadose zone storage. At the top of the box is land surface. The green box indicates the saturated groundwater storage, and at the top of the green box is the water table. Depth to water table is the distance between land surface and the water table. So the larger depth to water table is, the deeper below land surface the water table exists. The water table feedback zone is characterized by the sum of the root zone plus the capillary zone of the soil. So if the saturated groundwater or the water table is outside of this water table feedback zone, there is no influence on runoff, ET, and recharge. So we take a look at rainfall and how it's partitioned for this deep water table case. The size of the arrows represent the magnitude of the fluxes. We see that evapotranspiration is the largest, followed by recharge and runoff for this deep water table case. Groundwater ET is small or non-existent for deep water table. To contrast that, first of all, for this deep water table case, all of the fluxes are vertical through the vadose zone. we contrast that with a shallow water table case, we see that the water table has now entered the water table feedback zone. And so we're going to see a different partitioning of rainfall. See that evapotranspiration is now larger for the shallow water table case than the deep water table case. And groundwater ET is a larger fraction of the total ET. Runoff is now larger than recharge. All of these partitioning changes have occurred because the water table has moved closer to land surface, increasing soil moisture, causing the partitioning to change. This shows the tremendous influence of depth to water table, which is captured by an integrated model. We still have the vertical fluxes to the vadose zone, but now we have this water table feedback causing fluxes to rise up towards land surface through capillary action. So when is this simulation technology used? Well, first of all, hydrologic, hydrogeologic, climate, and anthropogenic attributes are factors. One of the number one causes is near surface depth to water table, causing dynamic feedback among processes for uplands, water bodies, and the groundwater system. Additional factors include changes to anthropogenic stresses or climate. Essentially anything that changes depth to water table, which includes pumping, climate, causes changes in the water table feedback and changes to the interfacial boundary conditions. In addition, there are strategic decision support needs that can influence whether or not to use this technology, where there's a need to increase simulation accuracy, capability, and flexibility, so moving from simulating the mean condition, flows and levels, to dry and wet conditions, either seasonally and or for annual conditions. The integrated model can provide that benefit. Also, to quantitatively partition changes to flows and levels into their causes, including climate, well pumping, surface water diversions, and land use, can be a benefit by using integrated models. Specific integrated model, called the IHM Integrated Hydrologic Model, dynamically couples all surface and groundwater processes, including uplands, water bodies, and the groundwater system, and their dynamic interactions. IHM uses or couples HSPF with MODFLOW to provide for this dynamic simulation of all processes. The Integrated Northern Tampa Bay Model, or INTB model, is a calibrated application of the IHM simulation engine. It covers 4,000 square miles of West Central Florida. 50% of the area is characterized by near surface depth to water table. 25% of the area is covered by water and wetlands. Approximately 500 million gallons per day of well pumping occurs in this region. Surficial and upper Floridan aquifers are well connected over most of the area by a leaky semi-confining unit, and because of that, surficial aquifer water levels, lake and wetland levels, and stream flow are influenced by pumping from the upper Floridan aquifer. Next segment started with discussing the Integrated Northern Tampa Bay Model, or INTB model, motivations for its development, and its conceptual foundations. The INTB model's motivations for its development goes back to the early 2000s. All of the factors involving integrated models and the need for integrated models, all of the boxes were checked for this area back in the early 2000s, including near surface depth to water table, climate anthropogenic stresses, reproducing dry and wet conditions. I want to talk a little bit more about partitioning of these causes into changes of flows and levels. At that time, there was a lot of understanding that climate, land use, and pumping all had caused to change the flows and levels, but it wasn't well understood just how much each of those caused those changes to occur. So this integrated model was an opportunity to provide that quantification. There's also a need to provide robust responses for plausible futures of climate and anthropogenic stresses and a combination of those. At that time, the applications were, list has since expanded, included optimizing wellfield pumping, supporting renewal and maintenance of well pumping permits, recovery assessment, and establishing minimum flows and levels. There are 3 calibration focus regions for the INTB model. First one included the Tampa Bay Water Consolidated well fields, shown in green. 75% of the Tampa Bay Water groundwater sources come from these well fields. Hillsborough River watershed, major potable water supply source and significant natural system resource. And then the Springs region, again, significant natural system resource for both the Hillsborough River and the Springs region. Anticipated MFL development was going to occur sometime after the early 2000s. Consolidated Wellfield is a major pumping center in the area. These 11 well fields, which are now 10, the North Pasco well field has been retired, are shown here in the corner, the relative location in central part of the study area. The history of the well field goes back to the 1930s when Cosme Wellfield began pumping. Since that time, all 11 well fields came online. About the early 90s is when the last well field started production. You note that there's a significant change in the pumping in 2003. This is when Tampa Bay Water brought surface water online as a potable source. This was in agreement through the arrangement of the Consolidated Wellfield permit with the Water Management District. See that this significant pumping change from in the 150s down into the below 90 million gallons a day. In the water use permit, by the year 2008, it was required that Tampa Bay Water limit the production from this well field to 90 million gallons a day. The INTB model covers the area of this period of time for high pumping and low pumping. This was done intentionally to understand whether the model could reproduce robust changes in flows and levels due to pumping changes. Topography of the model domain, elevations range from 0 to 300 feet with very mild slopes, 0.3% on the average. Estimated depth to water table was taken from NRCS data, soils data. Near surface depth to water table, less than 6 feet, was aligned with soils in the B to D classifications. Deep depth to water table was aligned with the A soils. It's in this deep depth to water table where it's blue, dark blue, where we have little, if any, water table feedback. The areas of green and yellow, shallow depth to water table is where we're going to see and have seen near surface water table feedback conditions. And so these estimates were aligned with what we were seeing from observed surficial water level data. Generalized land use in the area, 50% of the area is covered either by grass pasture or urban. Much of the grass pasture is transitioning to urban. Another 25% is covered by water and wetlands. And part of the robust calibration process was to assign properties to land use as the basis for model parameters. Surface connectivity of water bodies is shown in the graphic. Light blue shows the connected water bodies. The dark blue shows the conditionally connected water bodies. Surface runoff from the uplands is directed, 70% of the surface runoff is directed to conditionally connected wetlands. This is a significant component of the hydrology, the conceptual understanding of the area, since these isolated wetlands, conditionally connected, do not discharge to connected streams until they reach, the water levels reach the rim of the wetland, which means that during the dry season and early wet season, these wetlands do not discharge or contribute to downstream gauges. The other 30% of the upland area contributes to the connected system, so that when uplands discharge surface runoff to these connected wetland, these streams, the stream flow gauges see that runoff right away. Both the connected and the conditionally connected water bodies are connected to the groundwater system, either by recharging the groundwater system or by providing the groundwater system providing flow into these water bodies. Groundwater system transect here shows from the west, the Gulf of Mexico, to the east, down the spine of the middle of Florida, that there is a 3 dominant hydrostratigraphic units: Surficial aquifer at the top, intermediate confining unit or aquifer in the middle, and the Floridan aquifer, upper Floridan aquifer at the bottom. There is significant downward leakage over most of the area, but where we get closer to the Gulf of Mexico and Tampa Bay, where there are discharge points into major rivers, we see Floridan discharge upward into those features. There are generally 3 classifications for the Floridan aquifer in terms of its confinement: unconfined, semi-confined, and confined. The area to the south in this dark green is very well confined. The area in the middle in the bright green is moderate to poorly confined or moderate to high leakance. This is where the consolidated well fields are located in magenta. This area of Brooksville Ridge in the light brown is considered to be pretty well confined, with some areas of high leakance due to sinkholes that are present. There in the far north is completely unconfined Floridan, meaning that the sand that's on top of the limestone does not have a confining unit between it, and therefore the water table is coming from the upper Floridan aquifer. Groundwater system flow is shown here in the red arrows, similar between dry season and wet season. Essentially, the flow is moving from east to west toward the Gulf of Mexico with some interruptions. These interruptions occur due to discharge into major rivers, and also there's a significant low transmissivity region along the Brooksville Ridge, which redirects the flow, as you see shown by the arrows. Springs are shown in this map. See several springs in the Springs region, also which are Homosassa, Chesawitzka, and the Wekiwachi as the first magnitude. Some second magnitude springs in the south include Crystal River, Crystal Springs, Sulphur Springs, and then the Alafaya River is the Lithia and Buckhorn Springs. And this shows some spring sheds that have been delineated by the USGS for some of the northern springs in the region. Groundwater system, as I said, interacts with water bodies, and this map shows at flow gauges the fraction of base flow that exists in these locations. Low to moderate base flow fraction, characterized by blue and green dots at the Streamflow gauges, and the high base flow fraction, at least 10% or greater, is shown by the red locations. Significantly strong seasonal pattern in rainfall. You see that 60% of the rainfall occurs during the 4 months of the wet season. Annual rainfall can vary anywhere from 30 to 85 inches, and a mean of 52 inches. 2 major supply sources from the surface water system include the Hillsborough River and the Alafaya River. Again, we see a strong relationship, seasonal relationship, between rainfall on the streamflow and the aquifer levels. Interesting note here is that the Alafaya River has a smaller watershed contributing to it than the Hillsborough River, but has a larger stream flow because it has a smaller density of conditionally connected wetlands that store the water and keep it away from the connected stream system. Actual evapotranspiration accounts for 70% on the average of rainfall, but this percentage can change considerably. 55% for a wet year and 90% for a dry year indicating why streams go so low and water levels go down considerably during dry years. Evapotranspiration is a function of land use, prevailing soil moisture at the time, and depth to water table, which is influenced by pumping. The forested ET exceeds ET from grass by about 10 inches per year. The map you see on the right-hand side is a depiction of 37 inches of average annual ET distributed over polygons based on a target evapotranspiration long-term ET based on a combination of land use and depth to water table. Urban areas show the lowest evapotranspiration due to the high incidence or high density of impervious regions. Standpoint of temporal variability of ET, the ET for land use uplands max during the summer months of July and August. What's not shown is that water bodies max out in ET during the month of May because that's when the solar radiation is highest. Distribution of well pumping. We see here that on the right-hand side, the darkest squares show the highest density of pumping. Wellfields, public supply in the Hernando County area, and some irrigation areas for agriculture in South Hillsborough County. About 50% of the pumping from wells is used for potable supply. Another 25% is used for agriculture. Use and distribution of surface water diversions is used for all 5 categories of uses that are tracked by the Water Management District, as shown here on the left-hand side. There are also diversions in the model to account for environmental augmentation from wells into wetlands and lakes, and also transfers of water from wastewater treatment plants and industrial discharges into the stream network. Irrigation fluxes are also included in the model, account for groundwater and surface water sources. The density of irrigation fluxes is shown in the map, highest densities with the darker greens. Irrigation fluxes in the model are included for permitted uses of agriculture, landscape, and golf course. The model does not include irrigation for residential sources from potable. At this point, we'll take some questions again. Not seeing any questions at the moment. Anybody want to type a question, send it to me? All right, here we have some questions. First question is, what is the quality of the groundwater? Is the quality salty? Does it need to be treated before distribution? Quality of the groundwater is very good. The groundwater that's being pumped into the wells does not need to be treated or desalinated, does need to be treated to potable standards, but its quality is very, very high to begin with coming from the groundwater system. Next question is, what land use year is currently used in the calibrated model? That would be 1995. Water Management District and Tampa Bay Water are working on a project to modify the land use to year 2010. So we'll have essentially 2 separate models, one with the 1995 land use and one with the 2010 land use. Next question was about updating the land use year, which I've answered that question already. So I'll just speak a little bit more about that. Plan is to implement a 2010 land use for the model. And at some point between 2006 and 2010, there's going to be a transition from the 1995 land use model to the 2010 land use model in terms of the time series being assigned to each version of the model. Are there any other questions on this segment? Okay, if you have any other questions on this segment, you can submit those at any time. We'll move on to the next segment. This next segment is on the numerical model, which is based on the conceptual foundations that I've just described. The INTB model covers or includes 172 model basins. The highest density of these surface basins is over the Consolidated Wellfield and the Hillsborough River. Both topography and depth water table were used to define these model basins. Wherever there was a large difference in depth water table between an interim basin, it was separated into the shallow and deep part. Both daily and 15-minute gauges were acquired to define the rainfall input to the model. About 300 total gauges were used. Anywhere from 120 to 200 gauges were available per year. The gauge data were distributed spatially using Thiessen polygons. 15-minute time series of rainfall inputs were developed for each of the 172 model basins. Every model has a discretization scheme, and the INTB model also has that for its spatial elements. These spatial elements are called simulation units. First, start with HSPF, simulates the surface hydrology. For the pervious elements of uplands, there are 5 hydrologic response unit types, shown here based on land use: urban, forest, irrigated, grass pasture, mining, and other. 2 of those included irrigation flux, irrigated always, and grass pasture in a few cases. And then all of the imperviousness that exists in each basin is simulated by one impervious land segment. So we can have up to 6 different land segment simulation units in each basin, 5 pervious and 1 impervious. Water bodies discretized into these reach simulation units. We talked about conditionally connected and connected earlier. And then the routing reaches are a special case of connected, which are receiving water from connected reaches in upstream basins. All of the surface discharges from the uplands, pervious and impervious, are routed to these reaches in HSPF. We move to the groundwater system. MODFLOW simulates that using rectangular grid cells. Now there's a major difference here between the discretization scheme of using grid cells for MODFLOW and irregularly shaped polygons for both the land segments and reaches. I'll talk about that in a minute. And then the subgrid cell feature, called river cells, simulates water body conditions. And then because we have these disparate discretizations between HSPF and MODFLOW, we need to develop a scheme to allow IHM to communicate simulated responses between HSPF and MODFLOW throughout the simulation. And these are called IHM land fragments. Provides the opportunity for the models to talk to each other. In the same way, there are IHM water body fragments, called these integration units, allowing the reaches to transfer information to the river cells and vice versa throughout the simulation. This dynamic interaction that the IHM simulation code allows the INTB calibrated model to do. So a little bit more information about these fragments. Basin outline is shown in this dark black line all the way around. This is one basin of the INTB model. Inside of this one basin, you see all of the various generalized land use categories that I described earlier, all 5 of them, plus the water bodies. So all of these orange areas inside of this basin are urban. You can see that they're not necessarily touching each other, but the aggregation of all of these orange areas represent one simulation unit for the urban region. If we look at the dark brown areas, those are irrigated. Again, they're not touching each other, but aggregated together form one simulation unit in this basin. And the irrigated areas in this basin are simulated separately from the irrigated areas in the adjacent basins. Notice that they're irregularly shaped polygons. We overlay, for example, the grid from MODFLOW. We see that we have these disparate discretization schemes. When we overlay them together, we find that this is where the fragments come in. So this orange area represents one fragment of the urban land use that's linked to all of the other fragments that are part of the land segment of urban in this basin. In the same way, this occurs for the irrigated areas in dark brown. So this particular cell here has an irrigated, an urban, and a grass pasture land fragment, all of which make up the entire area of that cell. The same process is used then to define water body fragments. So we take the 5 generalized land uses, which account for the land segments for perviousness in the basin. We account for the imperviousness by another land segment. We combine in time pervious and impervious basin runoff and then distribute that runoff into the reaches based on how much upland area is discharging to each one of these different reaches within that basin. So again, there's 172 model basins, 5 upland land use categories. So there can be 5 pervious, up to 5 pervious land segments per basin, but overall there's 815 pervious land segments in the model. Some basins don't have all 5. 170 impervious land segments. 2 of the land segments do not have imperviousness. Surface discharge connectivity defines individual reaches by basin, and there are a total of 409 reaches in the model. Again, the land segment and reach parameters are tied closely to land use and soils properties, which provide the opportunity for robust calibration and reproduction of flows and levels. MODFLOW component discretization shows this grid system over 30,000 cells per layer. Variable spacing is used from 1/4 mile to 1 mile on a side. Highest density over the consolidated well fields. River cells provide the opportunity for flow exchange for water bodies between the groundwater system and water bodies. And the reaches of HSPF and the river cells of MODFLOW work together throughout the simulation, transferring integration information back and forth dynamically. Spatial distribution of this water body connection to the groundwater system is shown in these 2 slides, one for the Surficial Aquifer on the left, the other for the Floridan Aquifer on the right. Density is shown in green versus blue, blue being the highest density, where we can have multiple river cells in each groundwater grid cell. Note here that we have no connections in this area because this is unconfined Floridan. The Surficial Aquifer does not exist. On the other hand, the Floridan Aquifer has the high density of these water bodies because the Floridan Aquifer is the topmost active layer. Floridan Aquifer is also connected to the major rivers, as you can see here throughout the system. Boundary conditions for the 3 layers include active zone in this light green for all 3 layers, inactive for the moderate green, again, unconfined Floridan, so there is no layer 1 or 2 in this area. And then the dark green are constant head cells, which allows for upward discharge of the Floridan Aquifer into the Gulf of Mexico and Tampa Bay. There's no flow boundaries. Layer 3, the upper Floridan Aquifer in the eastern and northern boundaries, and then flux dependent head boundaries along the southwest and southern boundaries, which allows flow to go into or out of the model domain. As I said earlier, one of the very important features of an integrated model, and this includes the INTB model, is the ability for an integrated model to dynamically simulate recharge the groundwater system. So as rainfall changes, As the water table changes due to pumping changes, the recharge is going to change with it. Again, the recharge is a function of rainfall, soil moisture, and depth of water table. So as well pumping changes, it's going to modify recharge based on depth of water table changes. So essentially for the same soil, you're going to find that the recharge decreases as the depth of water table decreases. Talk a little bit about temporal discretization. The IHM, and therefore the INTB model, uses a sequential one-day integration time step. Within each day, HSPF simulates all upland and water body processes first. IHM takes output from HSPF and reconfigures that as input to MODFLOW, so that there's this dynamic change in how the groundwater system is affected by what is happening in the surface hydrology. MODFLOW simulates the groundwater system. IHM then picks up the output from MODFLOW, reconfigures that into an input change to HSPF so that the groundwater system also dynamically influences surface hydrology. As we cross this red line, we move into the next integration step or the next day of simulation. The right-hand side graphic shows a more detailed depiction of one integration time step. And we see that each of these components can simulate time steps in different durations. The land segments simulate time in 15-minute steps for the INTB model. The reaches simulate time steps in 1 day for a 1-day integration time step for the INTB model. And MODFLOW over 1-day periods breaks up time into 3 logarithmic steps. We see that HSPF runs first, followed then by integration by IHM, then MODFLOW, then integration M by IHM. We move back to the top to start the integration step over again. In the INTB model, this loop is 1 day long, 1 day long. The INTB model was calibrated over a 10-year period and then verified for another 8 years. Calibration targets included the target ET, which is an actual ET estimate representing long-term average annual evapotranspiration. Used 38 streamflow gauges, 7 spring gauges, and over 400 wells, roughly split evenly between Surficial and Upper Floridan Aquifer, to use as calibration targets. The model was peer-reviewed in 2013 by a nationally recognized team of modeling experts. Springflow targets and streamflow targets include the locations seen on the screen. The dark brown areas where the gauged watersheds are located over the 38 streamflow gauges. The 3 first magnitude springs noted in red were Springflow targets. In addition, Crystal Springs, Sulphur Springs, Lithium Buckcord Springs mounted to the 7 Springflow targets with significant time series. All the other ones that are shown here had sporadic values available that were used where possible. Well targets included those that are shown in red triangles for the Surficial Aquifer on the left and locations in the Upper Floridan Aquifer on the right. The green dots indicate data that became available from 2000 to the end of the simulation period, 2006, essentially over the verification period. So we were able to track how well the calibration did where we did not have calibration data during the calibration period. Documentation is significant for the model. The INTB model report published in 2013 and the peer review report also published in 2013. Both are available from the publications page of the IHM website. So at this point, we'll take some more questions. Question related to the first part. for the interflow in the vadose zone, is it simulated in HSPF? And will the simulation results also include interflow? So yes, the model does include interflow, and that term is simulated in the HSPF component. The INTB model does include interflow. Next question, has calibration been audited by updating land use to more recent? That's coming up in the next year to 2 years, where we'll be looking at a 2010 land use condition. What version of MODFLOW was used, and was MODFLOW Flux considered given the irregular nature of the domains? MODFLOW version used at this point is MODFLOW 96. We are working with the Water Management District in developing the next version, the next generation of the IHM, which would be IHM version 4. That version of the IHM will include MODFLOW USG, which will provide a very flexible framework for groundwater discretization in the future. Next question. For the groundwater simulation, is the river cell selected from the grid cell which contains water, or is the river cell newly built and is different from a grid cell? So a river cell is a subgrid feature of a specific grid cell. So you can have many river cells within one grid cell. And the way the INTB model is conceptualized and numerically defined is that the hydrologic response units for water bodies will all have separate river cells within a grid cell. For example, a lake responds differently than a wetland responds, and so therefore separate river cells are put into the MODFLOW part of the model to represent a lake versus a wetland within one grid cell. So if you have 4 or 5 wetlands in a grid cell and 4 or 5 lakes in the same grid cell, those 4 or 5 lakes will be aggregated into one river cell, and the 4 or 5 wetlands will be aggregated into a separate river cell for the same grid cell. How many parameters for groundwater and surface water models are there in the INTB model? That's the next question. For the surface water part of the model, there are somewhere in the order of 500 model parameters. For the groundwater part of the model, there are about 125 to 150 model parameters. Any other questions at this point? Okay, if you have any other questions on previous segments, go ahead and put those in. I will move on to the next segment. So our last segment is on example applications for the Integrated Northern Tampa Bay model. And you can read more about the applications that I will present and many others on the IHM website, either under case studies or under publications. First of all, I'll give you a list of the possible applications or the applications that have been used for the INTB model already. And they're broken down into 3 major segments: planning, regulation, and operations. And I won't have time this morning or this afternoon to talk about all of these. In fact, those that are highlighted in blue are the ones that I'll be spending a little bit of time with in this segment. First of all, for planning, it's been used to assess system sustainability for the Tampa Bay water supply system, used for climate variability and change investigations, for water shortage mitigation planning, assessing options for reclaimed water use in the future, to define depth to water table initial conditions for single regime surface water models, to support the establishment of wellhead protection areas and to define flow and nutrient loading to Upper Tampa Bay. From a regulation perspective, provides water use support, recovery assessment, establish and assess minimum flows and levels, and then assesses the permittability for new well pumping within the Hillsborough River watershed. And lastly, for operations, Tampa Bay Water uses it to optimize pumping operations from the well fields. First example that I'll talk about briefly is used for climate variability and climate change assessments. And the framework that you see in the graphic, describe a little bit. First of all, we start with general circulation models. These are the same models that are used for hurricane predictions. And their cells are very large, covering 200 to 300 kilometers, which amounts to about 12 cells over the state of Florida. So needless to say, there needs to be some downscaling to the INTB model domain. In addition, the climate models do not reproduce the seasonality of Florida climate very well, so there's some significant bias corrections that are required. Once the downscaling and bias corrections are completed, time series, again at 15-minute intervals for the climate, is input to the INTB model. Here it says IHM. And we run the model through its various scenarios of climate conditions, and then we can look at some impact assessments. This has been a partnership between Tampa Bay Water and the University of Florida for the last decade, and you can see a number of peer-reviewed papers that have been published over the last decade documenting that work. And we continue to work with the University of Florida to understand the effect of climate change on water resources, both for surface water and groundwater. Another example is using the integrated model to define depth to water table for a single regime surface water model, such as a flood event model. So the INTB model can define initial depth to water table conditions, a significant piece of the puzzle for a surface hydrology model. If there's interest in different pumping conditions, different pumping magnitudes, distributions, the integrated model can provide a very good estimate of what the depth to water table is expected to be over a range of rainfall conditions for that particular purpose for that surface water model. Now, if you're interested in a full depth to water table variability, a Monte Carlo simulation of rainfall, essentially defining a full range of possibilities of what the rainfall could look like in the future based on historical conditions, using those Monte Carlo simulations for future rainfall combined with one or more plausible future well pumping scenarios can provide a full understanding of what the depth to water table variability could be and how it relates to project objectives for this surface water model. Likewise, for streamflow changes, we may want to consider, what the streamflow would look like if the historical rainfall patterns continue in the future. We can develop a number of rainfall realizations. In this case, developed 1,000 rainfall realizations based on historical rainfall characteristics, all of the major characteristics. But we don't quite understand how many of those 1,000 rainfall realizations we need to capture the full variability of rainfall and its effect on a hydrologic system. So we do a numerical experiment with 6 sample sizes from 10 to 334 and 6 trials for each one. 2 pumping scenarios plus these Monte Carlo rainfall realizations are run through the INTB model, defines output for the no pumping case, one of the scenarios, and the pumping case, the other scenario, for all 1,000 rainfall realizations. So it's a lot of data. And what we find is that by the time you reach 250 random selections of the 1,000 rainfall realizations, we've captured the full variability of rainfall for any future condition, assuming no climate change, and 250 realizations also captures the full variability of streamflow. So we know how many we need at this point. And we can use this to assess changes to streamflow and the variability of streamflow relative to a pumping case. In this case here, we show the difference in streamflow for the Pithlichascody River for a case of pumping compared to no pumping. And the variability that we see is due to the rainfall variability over the full effect of any plausible future rainfall conditions. And these simulations used 20 years of rainfall time series, again at 15-minute intervals. The blue information is the full variability of streamflow given the pumping conditions. And for the same pumping differences, we see for two historical 11-year periods that the differences rolled along the bottom of the streamflow variability, the low points, and then crossed the median and went to the high. So these two particular years in the 90s and the early 2000s, these two particular periods, I should say, represented some extreme hydrologic conditions, both dry and wet. One of the other interesting things of looking at this data indicated that the highest differences in seasonal streamflow changes occurred during the summer months. What this told us is that runoff was a significant contributor to the streamflow change, not just base flow. Base flow changes were very small during the spring months. So what the integrated model can do that a single regime groundwater model or surface water model could not do is to capture the effect of this surface runoff element as well as the base flow together, defining total streamflow change. So by using the integrated model in this case and looking at the full range of potential future rainfalls, we were able to evaluate the influence of rainfall and minimize the risks of defining an unachievable NMFL or under and overutilizing the resource. So in summary, the INTB model can provide a robust application scenarios. The dynamic changes in flows and levels caused by one or more, a combination of rainfall, well pumping, and land use changes can be simulated by the integrated model in a way that can't be done as well for a single regime surface water or groundwater model. The integrated model, INTB, can assess changes to runoff, base flow, stream flow change, total stream flow, recharge, ET, groundwater levels, and lake and wetland levels, all within one model, and can partition changes into the various causes as I've described earlier. Are there any questions on the last segment or any other segment? So we have a question about climate. Are there any unified climate downscaled projections, in other words, rainfall or SLR, being developed for that whole region by UF perhaps? By whole region, I'm not sure if the questioner means more than the INTB model footprint, but over the INTB model specifically, the work that I'm aware of that's being done is what Tampa Bay Water is doing with the University of Florida. There is some sea level rise projections that are being done by some other agencies in the area, Tampa Bay Estuary Program and others, I believe. And Tampa Bay Water will likely be doing some of that on our own as well in the future. Do you have a graphical user interface for IHM to visualize the results? Is the next question. So we have a graphical user interface to input some results. Other results are dependent upon using a graphical user interface to input data into IHM, into HSPF and MODFLOW. So there's various third-party GUIs for that purpose. As far as visualizing the results, there are many post-processing plugins that IHM has that provide outputs for streamflow time series, for spatial overlays, spatial representation of heads, head differences, which can be ported into shapefiles and visualized, but there is not a graphical user interface tied into the IHM at this point to show those results. They're all shown through features like a Esri or other code that will show those features through a GIS. Any other questions? We have another 5 minutes or so if you have any more questions. Okay, we'll move on to the last slide. As a wrap up, I have one request. Please take 5 minutes to respond to the exit survey. Instead of exiting the webinar by dismissing the browser, exit the webinar by clicking exit at the bottom of the webinar control panel. Then the survey will appear. Please enter your responses and submit. To stay informed about IHM training opportunities and updates to the IHM and the INTB model, go to the IHM homepage and sign up as an IHM subscriber. A recording of this webinar will be available on the IHM website by about March 30 under training videos. By that same date, I expect to provide written responses to all questions submitted during the webinar. This concludes today's webinar. Thank you for participating.